I did hear a good joke yesterday. What do you call a retired coal miner? No. A retired coal miner. This one's for you. Are you even listening? You hearing this? Okay, retired coal miner. You call him Doug. Doug, that's a great name for a retired coal miner. Because it's past tense of dig. Oh my goodness. Come on, you're better than that. That was a knee slapper. You have to give it credit. What credit is due?
William Slapper.
Yeah, the bagel joke was good too. All right, so as I said, I'm not going to walk down the proof of this whole thing. Okay, you're trying to find the cosine of a sum of two angles. So for instance, what if I asked you for the cosine of 75 degrees?
I wouldn't know it.
You're going to be able to find the cosine of 75 degrees because you know information about a 30-degree angle and a 45-degree angle. Now, will I be asking you about the cosine of 76 degrees? No. We're going to be dealing with things that involve the 60s, the 45s, the 30s. Okay? So, and because this would be really complicated or would add another level to what we're doing, and I don't think we need to add another level to this, we will be dealing with degrees. Okay? So, I guess what that means, or should mean to you, is if we see a problem in radians, we are going to convert it to degrees. Okay, folks, you should be able to convert things to degrees. It will make it much simpler for you if you do. I think it is.
Wait, can we do it on our tablet?
Okay, now, basically the proof could be boiled down to this. And I'm going to have to, there's some cute way of remembering this that I'll have to ask. I'll have to ask Mrs. Bowen about it, because there's some clever way to remember this. But if you're taking the cosine of the sum of two angles, it basically boils down to the cosine, the product of the two cosines, minus the product of the two sines. The product of the two cosines minus the product of the two sines. Now, I do want to point out this. Is the sign the same or is it opposite? Is the sign the same or opposite? It is opposite, right? So, when they show you this, okay, it still has cosine, cosine. It still has sine, sine. But I want to point out to you this. Do you see how the plus is on the top here? But when you come over here, the minus is on top. Those signs go together. So if it's a minus in the original, it will be a plus on the right side. Do you get that? That they switch and the top ones go together and the bottom ones go together. For cosine, they will be opposites. Now, when we get to sine, we'll realize that they're both the same. What'd you say? What did you say? Sine, same. I like it. I like it. See, I like how you're thinking, man. It helps me. It helps me, helps you, helps them. Okay, yes, Miss Johnson. Okay, that goes back up to the proof that they were doing, which is also in your book. It has everything to do with the Pythagorean theorem. Every time you're doing these, if you want to go through the proof, it has to do with finding A, B, and C, D is a matter of going through your Pythagorean identities, and that's why they're subtracting the x's. Right here you can see they're subtracting x's. Here they're subtracting y's. And it's, you know, just a squared plus b squared kind of thing. And they're doing the same thing on the other side. And when you get down to it, you find out that the cosine of the angle can be figured out by looking at that. Okay, and there are signs involved in it, yes. It's just because of the x's and y's. All right, now, find the exact value of cosine 15 degrees without using a calculator. Okay, now, are you going to be adding two angles together? Remember, we're going to be using things like 30 and 45 and 60, maybe a 90. What combo do you think we should use to come up with? Should we be using a sum or a difference? I would say a difference, right? To get 15 degrees. Okay, you're not going to add any combo in that list and come up with 15, but you can subtract. So which one do you think? We have a couple choices here, but which one do you think we should use? We could use 30 and 45. Other people might use 60 and 45. It's okay. Both of those would work. So if we want the cosine of 15 degrees, that's the same thing as saying the cosine of 45 minus 30.
This sounds incredibly dumb, but could you divide cosine 30 by 2 and then cosine 15?
You're talking about a half angle formula, which we haven't gotten to yet, but the answer is yes. We could do it that way. All right? There's another formula in your future. You save that for a different day. Okay? I know. That's why you get a formula sheet. All right, now, if I use the formula that I see at the top of the screen there, we've got cosine 45, cosine 30, plus, right, because remember we changed the sign, sine 45, sine 30. Now all of those are pieces we know, because we know our unit circle. And don't you dare tell me we don't know our unit circle. Yes? Okay, so what's the cosine of 45? Root something. Oh, man, do we need a trip down memory lane here, folks? Oh, man, now I got to open up. Okay. Okay, remember the numbers 1, 2, 3, 4. Can't get through the kitchen door. Okay, so we take the square root of each one of those and divide by 2. That's because they're, you know, we've been working on our biceps so much. You know, you just hit the frame. That's when I have to step sideways, you know. 1/2. But those days are long gone, you know. Okay. Okay, so we talked about how these go in order. Right? So you had your 1/2, your radical 2/2, your radical 3/2, and your 1. So if we're at 45 degrees, what is the x value? Radical 2/2, yes, it's the one in the second one. Okay? So you definitely need to not forget this stuff, right? Please make sure that you don't. Yes, the unit circle of life. So the unit circle of life. Okay, yes. Little Elton John. Okay. Okay, that's not it, Chief. Okay, here it is. Okay, so we got radical 2/2. Thankfully, we got that. How about the cosine of 30? Radical 3/2. Plus, what's the sine of 45 degrees? Radical 2/2 times the sine of 30. 1/2. Sorry. Oh. So I'm running out of room here. What do you get when you multiply those two together? Radical 6 over 2 times 2 is not 2. 4, thank you. Plus, what's the product of these two? Too big a circle. Radical 2/4. Now, that is an acceptable way to write the answer, but let me show you another way. I will take either. Are we going to be given this formula? Of course we're going to be given this formula. Yeah, it'll be on the formula sheet. I understand as we keep adding more formulas, you know, your brains will explode. So I really want that not to happen. What? Okay, all right. Okay. See you next year. So either one of those would work. So you just got to use the formula and plug in the values. Yes. Because they are, that's a good question. They are not like radicals. We can multiply unlike radicals, but we cannot add unlike radicals. Just like we can multiply unlike terms, but we can't add unlike terms. Like if I asked you to add 2x and 5 together, you can't do it. But I can multiply 2x and 5 and get 10x. That's just the difference between multiplication and addition. Yes. What makes the radicals what? Okay. The only way you can have a like radical is if the radicand, there's a $1 million word for you, the part under the radical, they call it the radicand. So use that at parties. Okay. The radicand has to be exactly the same. For instance, if I asked you, can you add x and y together? Is there some way to combine x and y? You would say no, right? They're unlike terms. Just like radical 2 and radical 5. Those are unlike terms. You can't add those two radicals together no matter how hard you try. Now, could I get decimal equivalents on a calculator and add those together? Sure I could. I could do that. Okay? But as they stand right now in their more algebraic form, nope, I cannot add them together. What? Radical 2 is about 1.41. Radical 5, 2.24-ish. You can't add them in radical form, but you can add them in decimal form, yes, because you can find the real number approximates. They're not exacts, because remember, a radical of a non-perfect square goes on forever and ever and ever, never stops and never repeats. That's why we call it irrational. But we can get, you know, a rounded value of it and then add it to the rounded value of the other. It won't be technically exact, you know, but we're not launching something to the moon here, so. Okay. So example 2 here, prove the identities. So we're starting with cosine pi over 2 minus x. Obviously, this is a difference formula. So cosine pi over 2 minus x. And so we're going to, so that's cosine of the first times cosine of the second. And, oh, sorry, not equals. What am I thinking? What goes in the middle? Addition, nice. Sine of pi over 2, sine of x. Okay, now, you need to simplify that. Use your brain, figure it out. Folks, that's a big fat 0 right there. The x value at the top of the circle, remember? We got the top of the circle, we want the x value, it's a 0. Okay, what about the sine of pi over 2? That's a 1, right? Because it's the y value. Speak, Mr. Beaujolais, a little louder. I like what you're saying. Look what he noticed. Nice job. Because anything you multiply by 0, pretty much. 0 in the world of multiplication is a showstopper. I hope you understand that. That's right. That's the showstopper right there. When you multiply by 0, gone. Depends on whether you're on offense or defense. Okay? But anytime you end up plugging in zeros and ones, isn't that going to simplify your life a lot? Now, I hate to burst Mr. Beaujolais' bubble, okay? Because he was completely right. But did he know that was going to happen? Was he just cheating and looking ahead, or did he really put two and two together and think through that? I'm going to give him the benefit of the doubt and say I think he was thinking through that. All right? Because I'm not sure he was observant enough to... No, I'm just glad you were looking ahead and going, hey, 0 times cosine, gone. See, I think you did it right. I think you did it right. I don't think you were cheating.
I know B.
Okay. Well, personal friends. Okay, now, for some reason I didn't, you can't do example part 2, part B unless you have this formula. Okay, if you look back to it, example 2, part B is sine of pi over 2 minus x. We haven't shown you the formula for that. So either I screwed up and put example 2 in front of the formula, or the book did. One of the two. I thought I was doing okay, but maybe I'm not. All right, now if we look at this a little bit closer, you can see, and yes, I did not go through the whole proof of it. Okay, you can see that when you're dealing with sine, look what happens. Sine of the first angle, cosine of the second angle. Ooh. And then cosine of the first angle, sine of the second angle. But the signs are the same. So when you're dealing with sine, it's the same sign. If that makes any irrational thought in the world. Minus goes with minus. But it is a little different because it's a y value times an x value plus an x value times a y value. And like I said, I'll have to talk with, I know there's some cute way to remember that. Well, I don't know. That's what I remember. You could come up with your own way if you want to try to remember that. It will be on the formula sheet, yes. Because I knew you were about to ask that question, weren't you? Weren't you? Yes, you were. Use my creepy voice in the video. I know, man. Wait till you hear it on the video. You'll be like... Okay, let's go back to that example. See if we can squeeze it in the blank space right down here. What were we saying about me? Huh? Whatever. Sine pi over 2 minus x. Okay. Sine of pi over 2 minus x. So if we do the formula, what came first? The chicken? I knew somebody was going to go with that. All right, so sine pi over 2 times cosine of x minus cosine pi over 2 sine of x. Okay, I'll move it up here. All I'm doing is using that formula at the bottom. Using my pi over 2 for u, using my x for v, keeping the same sign in the middle. Are you waving to your fans or what? Okay. Okay, that's good to hear. Okay, what's the sine of pi over 2 again? 1. And what's the cosine of pi over 2? And what are we ending up with? Cosine x. Yeah, I know you told me it was cosine x, okay? I wasn't quite sure I believed your reasons for telling me, but yes, I did hear that. How do you look at it?
The units are like the periodic tables of trigonometry.
Kind of, yeah. Except we don't have any cool colors.
Chemists use periodic tables to figure out everything, whereas us trigonomists use
Trigonomists. That's a cool party word. All right, now, example 3. Letter A. When you look at this, do you believe that the first one is a sine or a cosine? All right. How do I know that it's a sine? No. You need to look at it and see that they're using sine and cosine in each one of the terms. That's what's telling you it's a sine. Now, what are we going to do with the 22 and the 13? Are we going to be subtracting them or adding them? We should be adding them, right? Because you told me that it was the same sign, right? So the answer to my question here is, if all I'm being asked to do is simplify them, then the answer to that question is the sine of 35 degrees. They didn't ask me, folks, to find what the sine of 35 was. They just wanted to know if it was a sine or a cosine and of what angle. Go to lunch.
Goodbye.
Goodbye.